is going to cover this discovery activity, and I would encourage you to actually work through it kind of on your own, and then if you get stuck you can refer to the video and just see if you can kind of make some of these connections. I'm going to go through this, and as I go through it, I'm not going to write in every answer to every question just for the sake of time, but I will post the key for the discovery so that you can refer back to it and kind of see what you compare yours and fill in any blanks that you missed if you need to make sense of it. Okay, so first of all, we're going to start this exploration. This lesson right here, this is called the binomial theorem. And the goal here today is that you can understand what the binomial theorem is and relate it to what we call binomial probability. Okay, so that's where we're headed. So we're going to start with something that we know and try and explore into something that is unfamiliar. So starting with this, it says expand each expression below completely. So remember that a binomial, when we started this, right, binomial meant an expression with two terms. So look at this guy has one term, two terms. All of these are what we would call binomials. So when we talk about binomial theorem, we're talking about this type of expression. So if we look at this first one, we say, okay, well, if I'm expanding x plus y to the 0 power, well, anything to the 0 power is just 1. So that one actually just simplifies to 1. Over here on the right, x plus y to the first power is just x plus y. Down here, x plus y squared, remember that's the same thing as x plus y times x plus y. So if I'm expanding this, I'm going to start to multiply through distribution or foiling, and I get x squared plus x times y, which is xy. I continue to distribute. I get y times x, which is yx, or in other words, xy, and y times y, which would be the y squared. So if I simplify that, I get x squared. These both are like terms, so that would be 2xy's plus y squared. So this right here would be the expanded form of that binomial. And then we could keep going. Remember, if this is to the third, that's x plus y times x plus y times x plus y. And the nice thing is that we just figured out that x plus y squared excuse me, is that. So I'm going to take these first two and just replace it by x squared plus 2xy plus y squared, because we already did that work. And then we still have one more of them here, so I'm going to times that by x plus y. You can put this in a box if it helps you keep track of terms, or again, just go ahead and distribute. So we're going to distribute here, and I'm going to get x cubed, x squared times y. Then I distribute the 2xy, so that's going to give me 2, and then x squared y. And then I multiply the 2xy by the y, so something similar, but 2x, and then it's y times y, so y squared. Okay, then we have this last term here to distribute, so y squared times x, or xy squared, and y squared times y would be y cubed. So again, if I just kind of combine some like terms, I have x cubed here on the first piece. It looks like I have x squared y and 2x squared y, which would be 3x squared y. I have 2xy squared and a y squared x. Those are the same thing, I just wrote them in different orders. So again, that would be 3 of those, because there's 2 there and 1 there. Xy squared, and then I have plus y cubed. Now we could keep expanding binomials and keep looking for patterns, but I felt like this was enough for us to kind of see a pattern. So first of all, we're going to look at the coefficients in a pattern with these. So we're going to write the coefficients of each of the expressions. So if we look at this first expression we created, there's only one value there. The coefficient is just a 1. For x plus 1 to the first power, if you notice up here, the coefficients here would be a 1 in front of the x, a 1 in front of the y. So again, we just have 1 and 1. The next one here, we have x plus 1 squared. So notice here we've got a 1 out front of the x squared. We've got a 2 and then another 1. So this one would be 1, 2, 1. And the next one, it looks like, was a 1 and a 3 and a 3 and a 1. So 1, 3, 3, 1. So it says describe at least two patterns you observe in the triangle of the coefficients. So just looking at these, there's a bunch of different patterns you can come up with. First of all, there's always ones, right, that are leading the coefficients, and there's ones as the last coefficient. So that's something maybe you noticed. Another one is that it's going 1, 2, 3 down this second diagonal. It also does the same thing going this way on the diagonal. Another one that maybe doesn't jump right out till we look at this in a bigger way, but you'll notice that anytime you take two numbers that are next to each other and you add them, it gives you the number right below. So 2 plus 1 is 3, or 1 plus 1 is 2. So this pattern we can use to fill in the rest of this triangle. Anytime we add it, we can figure out that number just below. So all different types of patterns. Another one, you can see these are powers of 11. There's just a lot of different powers there, or patterns, sorry. So this is what we call Pascal's triangle. So Blaise Pascal was a mathematician. It's named after him, and the pattern in the triangle represents the coefficients for a binomial expansion. So we're going to fill in this diagram, and again from what we had just above, and I started to fill this in just for sake of time, but remember ones go down the sides. So if that was a pattern we noticed, we could put ones all the way down the side, and we know that it always starts with a 1. Okay, the next thing we kind of talked about or noticed was that this second diagonal goes 1, 2, and then 3, and then 4. So we're going down this diagonal, 6, 7, 8, 9, and 10. The diagonal pattern went also the other direction. So 1, 2, 3, 4, 5. There's already a 6. I'm filling in a 7, 8, 9, and a 10. And then we can use that pattern by taking these numbers here. If I take the 4 and the 6 and I add them, remember that fills in that third one below, so that would be a 10. I can do the same thing here. 5 plus 10 is 15, 10 plus 10 is 20, 10 plus 5 is 15, and we can continue the same pattern to fill in the rest of this. You'll notice that with these patterns that we're using, it creates a symmetric triangle. So on the number of rows, right, that have an even number, the middle number is going to repeat. And then on these ones, it goes 1, 4, 6, 4, 1. 1, 6, 15, 20, 15, 6, 1. So they're symmetric on either side. So this is Pascal's triangle. And again, remember this represents what part of the binomial expansion? Just the coefficient. So if I could figure it out, though, what the coefficients, I could actually pull them from this without having to expand it out all the way, multiplying and distributing. Remember, and I'm just going to make point of this while we're on this triangle, that this was raised to the 0 power. The next row was raised to the first power. So when we talk about the row that it associates with, when you're thinking about, okay, well, where would I grab coefficients if I'm raising something to the third power? You want to choose the fourth row down, or in other words, the one with the 3 leading that second diagonal, right? If this is to the fourth power, there's that 4. If this is to the fifth power, there's that 5. So just don't forget that there's a 0th row. So the first row down, beyond that is the row 1. Let's talk about the coefficients really quick. So if I wanted to use this to expand something to the fourth power, that's great. If we look at the coefficients, which is number 4 on here, it says look back at your original work when multiplying it out and describe at least one pattern or rule that the variables appear to be following. So something I want you to notice as we expand this, you'll notice, and let's just look left to right, the first piece of the binomial, which in this case was an x, you'll notice that in the first term, it's raised to the second power. So it's raised to that power, right, that we were expanding this binomial to. Once it's raised to the second power, in the next term, it's raised to the first power, and then it's actually gone. So it goes 2, 1, and then x is gone. Notice the y values do just the reverse. It's raised to the second power here, to the first power in the middle, and then it's gone. Notice here over in the expanded binomial to the third power, kind of the same idea. You have x, that first piece of your binomial is raised to the third, then it's raised to the second, then it's raised to the first, and then it's gone. If your y value is raised to the third, to the second, to the first, and then it's gone. So as we expand these, one of the things you're going to notice is I'm going to talk about how I just take this first piece and I raise it to the power that we're expanding it to, and then we decrease that power as we move this direction. Then we take the second piece and do the same thing but reverse. We're going to decrease as we move to the left. So let's try a couple of these. I think that's what's on the next page. Awesome. So we're going to use these patterns to expand the binomial. So if I want to expand something to the 7th power, again, if I'm like foiling or distributing that out, it's going to take a while. So instead I can use this pattern. And so what I do is I look at this and I say, well, my value here is 7. So looking at the triangle, I would go to the row that has a 7 on it. So I'm looking at this row right here. And those would be the coefficients that I would start with. Now that's a lot of terms. Every one of those is a new term, right? We're going to put plus signs between them. So just practice writing it out. So we're going to start with 1. And again, I'm taking it from that triangle. So hopefully you can still see yours. And then I'm going to put a plus sign in front of each new one. So 1, then 7, then 21, then 35, then 35, then 21, then 7, then 1. So those again are just these coefficients from that 7th row. 1, 7, 21, 35, 35, 21, 7, 1. And those are going to be the coefficients on our terms. Then what I do is I take the first part of the binomial. So again, this would be x is the first term. So I would have x to the 7th here in the first term. And as I showed on the previous page, the exponents are going to then decrease in each term as I move to the right. So I'm going to have x to the 4th, x to the 3rd, x squared, x, and then x ran out of exponents. Then let's go the other direction. I'll put this in a new color so you can see it. Y is raised to the 7th power here, and it's raised to the 6th power here, and it's decreasing this direction. Now, one thing that I want you to notice as we go through this is if you look at all the terms now, notice that they all have 7 variables, so to speak. So this one has x to the 7th, the second one has x to the 6th, and y to the 1st. So that makes 7, 1 plus 6. This has 5 x's and 2 y's, so 7 variables. X to the 4th, y to the 3rd, also 7. And then just kind of reversing. So notice there's 7. That's important as we throw in the binomial theorem, that's part of the theorem, right, that we have accounted for all those variables. Now this is expanded as that goes. I guess I could write it closer together, but there's no simplification to be done on this one. So let me show you one that does have a little more simplification. Number 6 says expand the following binomial. This one's raised to the 5th power. So again, we would come back here and we would look at the row with the 5 here. And we would be looking at the coefficients 1, 5, 10, 10, 5, 1. So again, I'm going to space them out with a plus sign in between. So we're going to go 1 plus 5 plus 10 plus 10 plus 5 plus 1. Then I take my binomial and I look at the first term. It's an x again, so I'm going to do x to the 5th, x to the 4th, x to the 3rd, x squared, x, and then it's gone. Then this is the maybe a little bit trickier one. So this is no longer just a y value, it's a -2. So I have to do -2 to the 5th. And then I'm decreasing the exponent to the 4th. So it's the same thing I did with the y. It's just a numerical value. So we will, oops, I wrote 3. We will need to simplify this one more. So let's talk about how to simplify it. So again, this first term is already simplified. That's just 1x to the 5th, or we can just write x to the 5th. In this next term, you have a 5, but you also have a -2. So 5 times -2 gives us -10, and then we have that x to the 4th. So we're just combining that. In this next term, we've got -2 squared, which is really -2 squared is a +4. So you have 10 times x cubed times 4 is going to be 40, and then x cubed. In the next term here, you've got negative 2 to the third, which is negative 8. So you have 10 times x squared times negative 8 in this term, so that becomes negative 80 x squared. And we just continue that same idea. So here's our next term, negative 2 to the fourth is 16, and we have times that x and that 5. So if we go ahead and look at that as we are simplifying, that's also going to give us a positive 80 this time, and we have an x there. And then we have negative 2 to the fifth, which is just negative 32. So as you're simplifying, you just do one term at a time, and you can just break each piece of that down. Okay, so there's a few more example problems on here. I'm going to finish off this video doing one more example problem. I'll go ahead and do B, and then again, if you want to check the key, you can try out A and do that one as well. So again, I'm going to do B, and I'm looking at this, and I'm raising it to the fourth power, so I look at my triangle. Here's my triangle with 1, 4, 6, 4, 1 as the coefficients. So I start with 1, 4, 6, 4, 1, and then we continue to incorporate these pieces. So I have 2a, so that's the first piece, so I do 2a to the fourth, and then I decrease as I move this direction, so to the third squared. And again, don't get lazy and not put parentheses around them. That's where we make little mistakes in simplifying. And then we have this negative 1, so this is going to create some negatives in here. Oops, I have to raise it to the fifth. Oh, not the fifth, this time the fourth, the third, squared, and then it's gone. Okay, so let's simplify once again. So let's just do this first term. So again, remember an exponent goes here, and it's going to go here on the 2 and on the a. So 2 to the fourth is 16, and then a to the fourth is just a to the fourth. Okay, and then in this next term, I'm going to simplify each piece first. So the 4 is here, 2 to the third is 8, and then a to the third times negative 1. So I'm going to do 4 times 8 is 32, times negative 1 is negative 32, and then you're going to bring down that a to the third. So we're done with that one. So really test your exponent rules. Okay, so we've got 6 times, we've got 2 squared, which is 4, a squared, which is a squared, times negative 1 squared. If you square negative 1, it just becomes a positive 1. So that one's just 6 times 4, which is 24a squared. And then this next one, we've got, it looks like 4 times 2a times negative 1 to the third. Negative 1 to the third is just negative 1. So we've got 4 times 2 is 8, times negative 1 is negative 8, and then we'll bring that a down. And then lastly, negative 1 to the fourth is a positive 1, so this would be plus 1. So again, this would be our simplified version. And just to double check before I'm done, I look at my variables. A to the fourth, a to the third, a squared, a. Looks like we did great going that direction. Okay, that's just the discovery. Now we're going to tie it in just a little bit to our binomial theorem in just a second. I'm going to kind of finish out part of the discovery on this one. So it says, how many different pizzas can be ordered at a pizza palace if a pizza can be selected with any combination of the following? We've got anchovies, extra cheese, green peppers, mushrooms, olives, pepperoni, sausage, and tomatoes. So I'm going to relate this a little bit to probability. It says, how many different pizzas can you order with 8 toppings? So you think about it, and you're like, well, only one. I can order all 8 toppings, or not, but that would not be in a pizza with 8 toppings. So there's only one pizza, and it has all 8 toppings on it. It says, how many pizzas can you order with only 1 topping? So if you think about that, you could choose the anchovies, or the extra cheese, or the green peppers, and you just choose one at a time. That would make 8 different pizzas. How many pizzas can you order with 7 toppings? Same idea. You could either leave off the anchovies once, then leave off the extra cheese the next time. And if you leave off exactly one, you'll be able to make 8 pizzas once again. So we can continue kind of this pattern, and you'll realize, and I don't know from our last homework, that essentially what you're doing is you're taking 8 and you're choosing 7 toppings, or you're taking 8 toppings and you're choosing 1 topping for each pizza, or you're 8 and you're choosing 8. And if we check these in the calculator, when we do 8 to choose 2 toppings, we end up getting 28 pizzas. And we could list all of those. It's quite a few. With 6 toppings, that would be 8 choose 6. And that would also be 28 pizzas. And the next question just says, locate the values of your answers to questions 7, 8, 9, and 10 in Pascal's triangle. And then circle those values. Describe the relationship between the various numbers. It says on the triangle below, so I was going to go forward and see. So I believe it means the one on the previous page. So if you look at where our answers came up here on our triangle going back, there was 1 pizza, there were 8 pizzas, there were 28 pizzas. So you'll notice everything's coming from this row right here, and the reason being is because we are choosing from 8 toppings. So you can imagine this is with where we're headed next, right? Okay, well that was with 2 toppings, this was with 1, and this was with all 8, or in other words, no toppings. So the next one with 3 toppings, we would imagine there'd be 56 pizzas. With 4, it'd be 70, and so on and so forth. 5 would drop back down. So as we jump over here, it asks us to describe the relationship between the numbers, so they all come from the same row. And then without drawing out the sample space, how could we decide what it would be with 3 toppings? So that's what we kind of looked at there. We know that it would be the next number on that row, which would be 56 pizzas. So if we were looking at 4 toppings, again, that would be the next number on that row, 70. And it would definitely be a combination, because it doesn't matter what order we put those toppings on, there's still that same type of pizza. And then notice that it came back down as we were moving through the row because it's symmetric, and we got 56. So in all, if we were looking at how many pizzas we could order, we would add up that whole row. We would have 1 plus the 8 plus the 28 plus 56. And we would go all the way down the row. And essentially we would end up with 256 different pizzas that we could order. So just looking at that triangle, what we wanted to do is just kind of connect Pascal's triangle with the combination notation. So notice I can create or represent the triangle with the combination notation. I could come back and I could create that 8th row. It says the first 7 rows. I'm only going to create a few, but I do want to create this 8th row since that's the one that we had up here. So that would be like 8 choose 0, right? That's 0 toppings. There's 1 pizza you can order that way. Then the next one was with 1 topping. So 8 choose 1 would give us that 8. 8 choose 2. And we could continue. 8 choose 3. This would represent the 8th row. I probably should have wrote this smaller. It's going to be huge. 8 choose 4. Oh, now I'm going back down suddenly. Yikes. 6. 8 choose 7, and 8 choose 8. So this represents all of those numbers essentially up there. And so we could create the Pascal's triangle. The first one would be essentially 0 choose 0, right? There's only one way to do that. The next row would be 1 choose 0 and 1 choose 1. The next row would be 2 choose 0, then 2 choose, oh, that's a big 2. 2 choose 1, then 2 choose 2. 3 choose 0, 3 choose 1, 3 choose 2, and 3 choose 3, and so on and so forth, and we could create the triangle all the way up through that. And this is going to help us with our notation that we're going to use with the binomial theorem, and it helps us to connect the binomial theorem a little bit to binomial probability, because we're going to see this notation, and this combination notation is going to represent the coefficients in our binomial expression.